Hello everyone, welcome back to GVM Success Path. In today's video, we will be learning about one of the most important and beautiful results in algebra, Boolean algebra, that is the representation theorem. The theorem tells us that every finite Boolean algebra is just like a power set, simple and structured. I'll explain it step by step in a clear and intuitive way so you'll never forget it. So, if you are a student who wants to deeply understand mathematics, not just memorize it, you are in the right place. If you are new here, don't forget to subscribe GVM Success Path and click the bell icon so you never miss a topic from your M.Sc syllabus. Let's get started with this powerful theorem. Now let's see the statement of the theorem. Let B be a finite Boolean algebra and let A denote the set of all atoms in B. Then B is isomorphic to power set A, that is B mean join is isomorphic to power set of A, intersection and union. So first let's see what is Boolean algebra, what is this atoms, what is isomorphism, and what is this power set A. Before going in deep into this representation theorem, we must know about these terms. So let's see one by one. Now let's first see what is Boolean algebra. Boolean algebra is a set with operations like and, or, and not, satisfying certain rules like distributivity, identity, and complements, etc. Let's see what atom is. An atom is a minimal non-zero element in the Boolean algebra. That is, like in simple terms, it is the smallest building block, just like prime numbers for multiplication. Now let's see about power set. Power set is the set of all subsets of A. It forms a Boolean algebra with operations union, intersection, and complement with respect to the full set A. Let's see about isomorphism. Isomorphism is the structure preserving map function between two algebras that keeps all operations intact. That means they are essentially the same in terms of structure. Let's break down this representation theorem in easy words like any finite Boolean algebra can be rebuilt or represented using the power set of its atoms. Because this theorem is very powerful and an intuitive way, because it allows us to study all finite Boolean algebra using simple set theory. It also gives a way to visualize any finite Boolean algebra using sets and subsets. Let's see the proof of the theorem. Let B be a finite Boolean algebra and A be the set of atoms in B. We want to prove that B is isomorphic to the power set of A. That means every element in B behaves like the subset of atoms and all operations like and, or, and not that are preserved. I hope you understand. Now we are about to see the proof of this theorem, so don't skip the video. First step of the proof of the theorem, we are going to define a function h. That is, h of v is equal to set of all A belongs to A such that A is less than or equal to V. That is, for any element B belong to B, we define h of v as h of v is equal to set of all a belongs to a such that a is less than or equal to v. What does this mean? This means take all the atoms that are less than or equal to v into this set h of v. I hope you understand. We are taking all the elements that are less than or equal to v in this h of v set. So h of v is the subset of atoms that fits in power set of atoms A, that is P of A. As the next step of the proof, we are going to show that H preserves these operations like AND, OR and NOT. First, let's see for AND operation and to intersection. Okay. We want to prove that H of V join W is equal to H of V intersection H of W. For this, let A be an atom. Then A belongs to H of V intersection, join W. That is, we are taking an atom from this A. This implies A is less than or equal to V and A is less than or equal to W. Before that, we are about to know that from this equation, A is less than or equal to V intersection or V join W. A is less than or equal to V join W. That means A is less than or equal to V and A is less than or equal to W. This means A belongs to H of V intersection H of W. Therefore, we showed that we are taking an atom from this set and we showed that atom belongs to this set. So, this is proved. Let's see for OR operation. Now, let's see for OR operation. We want to prove that H of V meet W is equal to H of V union H of W. For that, we are taking an atom A. Then A is less than or equal to V, A is less than or equal to W. This implies A is less than or equal to V meet W. Therefore, A belongs to H of V and H of W, their union. This implies A belongs to H of V meet W. This shows that H preserves OR operation. Now let's see for complement operation. We want to prove that H of V complement is equal to A by H of V. That is, the atoms below V complement are exactly those atoms in A that are not in H of V. I hope you understand. I'll repeat this. The atoms below V complement are exactly those atoms in A that are not in H of V. Let's take atom A belong to A. This implies A belongs to H of V dash. Therefore, A is less than V dash. Since A is an atom, A is less than or equal to V, A is less than or equal to V dash. This implies A is equal to 0, which is actually not possible. So, A can't be below both. Therefore, if A belongs to H of V dash, then A does not belong to H of V and vice versa. So, H of V dash is equal to A by H of V. Next, we want to show that H is 1 to 1, that is injective. To prove that H is 1 to 1, that is injective, we are assuming that H of V is equal to H of W. That means both V and W have same atoms below them. But in Boolean algebra, an element is completely determined by the atoms below it. So, if the atoms are below both V and W, then V is equal to W. This means H is injective, that is 1 to 1. To prove H is onto, that is surjective, let's take any subset C, that is C subset of A, and also take V is equal to R of atom C, that is R of atoms is denoted as like this. You know it, right? So what does this equation means? Take all the R atoms, that is take R of all atoms in C. Take R of all atoms in C. That is this equation. That then H of V is equal to C. So every subset of atoms comes from some element in B, right? Hence, H is surjective, that is onto. So here arrives the final conclusion of the proof, that is H is Boolean homomorphism, as we proved that it preserves and or and complement operations. Also, H is injective, that is, no two elements map to the same subset. Also, we prove that H is surjective, that is, covers all the subset of atoms. I hope you understand. Therefore, we arrive at a conclusion B is isomorphic to power set of A. Hence, the theorem is proved. So that's it for today's lesson on representation theorem in Boolean algebra. I hope you now understand how every finite algebra can be represented as power set of its atoms, a simple but powerful idea that makes abstract algebra more visualized and relatable. If this video helped you, please do like, share, and most importantly, subscribe to GVM Success Path for more clear and concept-based explanation, especially for M.Sc Math students. And don't forget to hit the bell icon so you never miss an update. See you in our next video. Keep learning, keep growing. Bye.